I'm Jake O'Neill, creator of Animagraphs, and this is how a steam locomotive works. I've chosen the Union Pacific Big Boy as my source inspiration. However, I've also made many period-correct generalizations for the sake of teaching. Big Boy came to be in late 1941, at the latter end of the steam era, as one of the largest and most powerful steam locomotives ever produced. 25 Big Boys were put to work between 1941 and 1944. To give you an idea of its size, here's an Old West style locomotive from the mid-1800s, placed side by side. Despite the many advancements in technology from earlier steam engines to our model, they share the basics for generating steam power. The engine and tender combined weigh about 604 tons. You'd need something like 4 modern engines to pull a 5-mile train like Big Boy could do alone. Top speed is around 70 miles per hour on level track. Coal, wood, or even oil in later years is used as a source of heat. To boil water. The volume of water expands as it turns into steam, creating pressure that can be used to do work. In this case, steam pushes pistons back and forth to rotate the wheels, releasing its pressure and temperature in the process. The used up steam is exhausted from the train. A tender rides behind the engine with the fuel supply and a large water tank. Now let's get into the details of each system, starting with the firebox, where coal is burned to make heat. At the bottom of the firebox, a bed of coals sits on top of special movable metal grates. Shaking the grates releases spent coals and ashes. Or they can be fully tilted to dump the coals entirely. Waste falls into ash pans below, with doors that open between wheel axles to fully clean out the firebox. Air for combustion enters through openings at the top of the ash pans. Specially sized gaps between the metal grates allow a predetermined rate of airflow up into the coal bed. The thick steel sides of the enclosed firebox are called sheets with side and rear sheets. The tube sheet up front and the crown sheet on top. Boiler water surrounds these sheets. There are circulator tubes extending from the sides and up through the crown sheet to increase water circulation in the boiler. These tubes also support the brick arch. The brick arch directs heat, flames, and smoke back over the fire as it travels out of the firebox for cinder and spark reduction, even heating, and more complete combustion overall. Billows of black smoke out of the smokestack indicate inefficient combustion with unburned particles in the exhaust smoke. Coal is fed into the firebox through an automatic stoker, which we'll examine later. There's a fire door in the cab so crew can closely monitor and tend to the fire. Some air also reaches the fire through this opening. Hot exhaust smoke travels through many tubes at the front of the firebox. On its way toward the smokestacks at the front. Normal operating temperature is in the 1,800 to 3,000 degrees Fahrenheit range. The boiler surrounds the firebox and is mostly filled with water. Intense heat from the firebox boils this water, turning it into steam which expands, exerting as much as 300 pounds per square inch of pressure on the boiler walls. Many rows of stay bolts between the firebox and the boiler exterior help components keep their proper shape against these incredible pressures. Water must cover the firebox sheets at all times when the train is underway. The crown sheet, being closest to the top of the ever-changing boiler water level, is most vulnerable to exposure. The red-hot fire within will easily melt bare metal, causing boiler failure and rapid release of the ultra-high pressures within, resulting in a massive explosion. The tubes through which hot firebox exhaust flows offer much more surface area for heat transfer to boiler water. There's a steam dome at the top where steam collects and flows out of the boiler. Blowdown valves help clean the boiler interior. Big Boy has a separator type blowdown at the top rear of the boiler which uses centrifugal forces to separate steam from sludge on its way out. It's electrically managed from a signal foam meter, which we'll see in the cab later. And a manually operated blowdown valve near the bottom. Contaminants and particles in water may coat boiler surfaces for less efficient operation over time. Contaminants can also cause foaming, where the water foams as it boils, which in turn leaves water content in the resulting steam. When the blowdown is operated, high-pressure water or steam, depending on which type of blowdown is in operation, blasts to the outside, carrying contaminants with it. Pure steam is a gas with no water in it. It's invisible to the human eye. Steam you can see still carries some water content or droplets. And most importantly, steam can be compressed, while water is not compressible at all. The dizzying tangle of steam-driven components aboard our locomotive are all based on compressing or expanding steam. If these moving parts attempt to compress water, they're likely to break instead. Continuing with the boiler, there are safety valves near the steam dome to let off excess pressure. Water flowing into the boiler must be pumped or injected in to overcome boiler pressure. For safety and efficiency, there are redundant feed water components. There's a mechanical pump under the left or fireman's side of the cab. The main water connection from the tender is nearby. At the front of the engine, there's an exhaust steam injector, which is a clever device that uses hot exhaust steam to operate. I've created a simplified visual to show you how it works. Exhaust steam from cylinders enters the injector at high pressure but low velocity. It passes through a narrowing tube where its pressure is converted into high velocity. This steam jet causes low pressure in the following chamber, which acts like a vacuum to suck water into the stream from a water supply nozzle. The hot steam mixes with water and condenses for a fast-moving stream. A second steam nozzle stage further intensifies the process. The cone-shaped passage gradually widens as it approaches the outlet at the other side. And all that velocity imparted to the water stream turns back into pressure again so it can be injected successfully into the boiler. Also worth noting, there's a supplementary inlet to admit live boiler steam as needed to keep the injector running. There's a second water injector mounted under the engineer's side of the cab that runs on normal boiler steam. Water from injectors enters the boiler through one-way check valves near the front. A turret mounted at the top back of the boiler serves as a connection point for the many supporting appliances needed to run the locomotive. things like gauges, pumps, and more. Now, let's follow the steam as it leaves the boiler. There's a steam dryer mounted in the dome. Outflowing steam passes through the dryer, which spins a wheel with fins to fling water droplets out of the stream for an initial water separation stage. Steam then travels through the dry pipe to the superheater unit, which is suspended outside of the boiler in the smokebox area. The superheater does just what it says, heating the steam even further for a pure, dry gas. Superheated steam can also do more work before it cools and returns to a liquid. The steam produced inside the boiler is just at its boiling point and needs to be completely separate from the mass of water for proper superheating. Some of the previously shown tubes here are larger tubes called flues. The superheater has a network of its own tubes which extend into these flues for close contact with super hot Firebox exhaust. These tubes are folded over for added length and maximum heating time. One down and back run is called a unit. The now superheated steam leaves the superheater through a multi-valve throttle assembly. A very long throttle rod extends all the way from the engineer's side of the cab to a pivot joint, eventually entering the smokebox here. As the engineer advances the throttle lever, a row of valves opens gradually in turn for greater control over the quantity of steam allowed to exit the superheater. This steam travels out through steam pipes called branch pipes to the cylinders and pistons, which we'll see in a minute. The superheater sits in a large forward chamber called the smokebox, which has its own set of critical tasks to keep the train running smoothly. A violent mix of smoke, cinders, and glowing embers shoots out of the flues and tubes into this compartment. Baffle plates make a winding passage to slow these flying particles and reduce wear on forward parts. At the end of this path, there's a metal screen to filter out hot embers. Any burning material escaping the smokestacks can cause trackside fires and otherwise contribute to pollution. As steam engines grew in size over the years, smokestacks extended further down into the smokebox for clearance through tunnels and so forth. There are two smokestacks here, which are centered above blast nozzles. The used up exhaust steam from drive cylinders exits through these nozzles on its way out through the smokestacks. This configuration turns otherwise wasted exhaust steam into a draft appliance. The powerful jets generate a tremendous suction force in the system to draw more air into the firebox for a livelier fire. Blast nozzles separate exhaust for increased contact area with the fast-moving jet streams. The smokestacks are flared at the bottom, with secondary openings for the same reason: increased opportunity for smoke to be drawn into the exhaust steam jets. A combination of smoke and steam exits the stacks, which are designed to lift the exhaust high enough above the train to prevent visibility issues for the crew. Now, let's return to the superheated steam and see how it's put to work. Steam flows through pipes along the exterior of the boiler to cylinders which are cast into the locomotive frame. Big Boy has 4 cylinders, 2 at the front and 2 about halfway down the length of the locomotive. Pistons inside these cylinders are driven back and forth by compressed steam as it enters, expands, and exits the cylinder chamber. piston rod is anchored to the crosshead, which rides in its own supporting channel. From the crosshead, the sturdy main rod translates the piston's linear back and forth movement to rotation at the wheels. Steam delivery is managed by the nearby piston valve. Superheated steam flows in at the center. The piston valve keeps it perfectly contained. As the piston valve travels, it exposes a port which allows steam to flow into the cylinder, pushing the piston in turn. As the piston reaches the end of its stroke, the piston valve has also moved, exposing that same port again, while also revealing an exhaust passage at its end. The piston moves forward as steam is allowed to exit through this exhaust passage on its way to blast nozzles and smokestacks. This same process happens at the back of the cylinder to push the piston forward again. The piston and valve continue their synchronized movements, exchanging fresh superheated steam for spent exhaust as the train chuffs down the track. The relationship between piston and valve is controlled by the valve gear. This system can even reverse valve timing entirely, sending the piston, wheels, and thus the entire train into reverse. Let's see how it works. The particular setup shown here is called a Walschaerts valve gear, which is just one configuration among various devised during the steam era. A crank at the wheel imparts a continuous back and forth motion to the expansion link through a connecting rod, and through another rod to the valve. There is some piston movement blended into the system here through a couple linked levers at the crosshead. Without getting too complex, this bit further alters valve open and close timing for better performance. It's mesmerizing to watch, isn't it? Back at the expansion link, there's a channel with a sliding pin. This is where the reverser lever connects to the system. When the engineer in the cab moves the reverser lever, the pin also moves. As you can see, this changes the position of the valve in the system, and therefore its timing. At each extremity, valve timing is opposite its previous setting. As the pin nears the neutral or center position, the valve moves less and less, whether on the forward or reverse side of the channel, to the point where its only movement comes from slight piston effects at the very center. Now, let's see things happen in regular motion. We're traveling forward and the pin is at the bottom of the expansion link. As the reverser lever moves, the pin travels towards the top of the channel. Now the valve's timing alters, so it fills the opposite side of the cylinder with fresh hot steam, and the system moves into reverse operation. This system also lets the engineer deliver less steam for more economical operation. For a hard pull when starting to move the train, the lever may be more towards the full forward position. As the train gets underway nicely, the engineer can back the lever off some, since less steam may be needed to keep the train going forward. The reverser lever has a power reverse cylinder that uses compressed air to move the lever. With almost innumerable moving parts, lubrication is an immense task. There are front and rear mechanical lubricators on both sides, which are driven through a linkage to the valve gear. Power from the main rod is distributed to the driving wheels through connecting rods. The wheels have additional weight added opposite this connection point for more balanced rotation. To properly take in Big Boy's wheel layout, let's zoom out and look at the whole frame. Big Boy is an articulated locomotive, where the two main frame sections are joined by a large fortified pin at the midpoint, allowing these sections to move independently of one another. Without this arrangement, the engine would be too long to navigate existing railway curves. There's a leading truck, with a connecting pin which supports the front frame section. And the rear frame is supported by a trailing truck. The rear frame directs the locomotive into curves while other frame components pivot to fit. The steam piping at the front has ball joints to allow movement with shifting frame sections. The locomotive in full articulation is an impressive sight, with the huge boiler and front end hanging far to one side over the lead truck. The wheel arrangement means Big Boy is classified as a 4884 locomotive, with 4 leading wheels, 2 sets of 8 driving wheels, and 4 trailing wheels. Suspension. A system of leaf springs where space allows, and coil springs supports the wheels and axles. Suspension for each individual wheel set is linked front to back through equalization bars, such that if one axle dips or rises, the load is shared through the system. It's also equalized side to side through beams at the front and back of each frame section. There's an equalization beam which extends from the front frame section to rest at the center pin of the lead truck, which has its own suspension components. The trailing truck has suspension equalization bars at each side that extend from the main rear frame section, along with its own system of leaf and coil springs. Axles are fitted with a lateral movement device for cushioning as they move fractions of inches side to side. Frame sections are designed to pivot around a rigid point. For example, the third driver wheel set is the pivot point for this frame section, and each subsequent axle is allowed greater lateral movement from this point. The leading truck's center pin has its own special centering device. Again, there are various ways to accomplish this goal. For our setup, the main center support platform is suspended on pairs of pins that ride in an arced slot. As the truck and center pins sway with engine movement, the hanging arms can rock to accommodate themselves as necessary, but will favor the centered position. Brakes. The brake system runs on air pressure. Air is generated by 2 steam-driven air compressors mounted to either side of the pilot at the front. These are cross-compound units with high and low pressure compartments for both steam and air. Separating these stages makes for more efficient operation overall. Aftercoolers, one for each compressor, are mounted underneath the forward platform. Cooling fins dissipate heat as hot compressor air travels through the tubes, on its way to storage reservoirs at either side of the boiler. There are 2 brake cylinders on each main frame section. Arms extend down to the brake armature, which links everything together. There are adjustment points throughout. Brake shoes are situated at the back of each driving wheel set and press against the wheel's metal tires to slow the train. The trailing truck has its own brake cylinders and linkages to actuate brake shoes at each wheel. The air compressors generate braking air for the whole train, with controls in the cab to apply brakes for the locomotive and tender only, all cars together, or some combination of both. Also at each driving wheel, there's a nozzle for sand, which is blown at the wheel and track to provide increased traction between smooth metal surfaces when necessary. Large containers called sand domes sit atop the boiler shell, with plumbing that extends downwards. There are valves to control sand flow and admit pressurized air into the system. As for other items visible at the exterior, there's a headlight at the front with 2 sets of number plates. The bell is hung at the front instead of on top for clearance, since the boiler is so large. There's a steam whistle nestled behind the smokestacks. Now let's head rearward for a look inside Big Boy's cab, which was among the largest of its day. There are 4 seats for the engineer, fireman, head brakeman, and a spare. The engineer is in charge of safe train operation and the locomotive itself, as well as visibility on the right side of the train. The fireman handles steam production, watching the boiler and its associated systems closely throughout continuously changing power demand. The fireman is also in charge of left side visibility. The brakeman couples and uncouples cars and also watches for journal box or hot box fires, where bearings in car axles may heat up and catch fire. The brakeman also handles track switches at the front of the train. The boiler extends right into the cab, with the back head forming the cab's front wall. It's covered with critical instruments, gauges, knobs, and more. Let's look at the controls a little closer, starting with the engineer's side of the cab. The knob at the right front corner controls the previously shown blowdown valves for cleaning scale out of the boiler. Nearby, we see the reverser lever, which controls the valve gear. The sander control valve is to the left for blowing sand on the rails. Up above these controls, there are dual gauges to monitor brake system air pressure in cylinders, pipes, and reservoirs. Moving towards the engineer's seat, there's the throttle lever, which actuates the very long throttle rod running down the side of the boiler. Up and to the right, there's a knob for the headlights. The whistle pull chain hangs nearby at about shoulder level. Moving downward, we see the air brake stand. The leftmost lever controls brakes for the entire train. The smaller right lever controls brakes for the engine and tender only. Down to the left side of the seat, there's a lever to control the engineer's side steam injector, which injects water into the boiler. At the far back corner on the engineer's side, there's a knob to admit water into the steam injector. Moving back to the engineer's view, let's examine the controls attached to the back head. There are knobs to open or close cylinder cocks, which allow any water to drain from cylinders. For example, if the train has sat and cooled for a while, condensation in the system may have drained by gravity into the cylinders and needs to be released. There's a rail washer above that, which was uninstalled later on in Big Boy's service life. The yellow triangular knob controls emergency steam to the power reverse cylinder. There's the main boiler pressure gauge, and a positionable lamp sits nearby. At the center of the back head, there are 2 sets of sight glasses for the engineer and fireman respectively. It's critical critically important to be aware of the boiler's water level at all times during operation. Sight glasses are placed at a vertical offset for redundancy and for versatility in reading water levels in varying conditions, for example when on an incline or a decline. The long copper tube at the top admits steam from the boiler. Its length allows steam to cool, resulting in a steady shower of condensate flowing from the top of the glass to keep it clean and show that it's functioning properly. There are blowdown valves for individual sight gauges and for the water columns that serve each pair to clean components and prevent clogging. At the engineer's side, there are 3 valves at the top, middle, and bottom of the sight glass monitoring range called tricoques. When opened, these valves should emit steam or water as indicated in the sight glass to verify sight glass accuracy. Maintaining the proper boiler water level is simply too important to leave to any kind of chance. Moving along, the dynamo valve controls the steam-driven DC power generator, which supplies electricity for onboard lights. There's a foam meter above that with lights to indicate safe or unsafe foam levels inside the boiler. There's a blower inside the Smokebox that can be used to augment draft and circulate more air through the firebox. Let's continue towards the fireman's side of the cab and backhead. There's a valve for controlling the train's steam-powered heating with a nearby gauge for monitoring. The leftmost gauge is a redundant boiler pressure gauge. Beneath that, a gauge to monitor exhaust steam injector pressure. To the right, there's the Stoker pressure gauge. We'll look at the automatic Stoker in a minute. Moving down, we see the exhaust steam injector starting handle. And further down still, there's an overflow indicator. And water regulator valve for the same injector. At the midpoint, there's a collection of valves to control the automatic Stoker, which has individual steam jets to blow coal to various parts of the firebox. At the bottom, there's a collection of valves to control water sprinklers for washing the ash pans. Moving back to the center, we see the automatic fire door. It has an air cylinder to aid opening and closing the heavy door. Rotating the lever turns a set of gears so both doors open at once. There's also a foot pedal to actuate these doors when shoveling coal manually into the firebox. Now let's head outside the cab for a look at the tender. The tender carries coal and water, which the locomotive needs to operate. The water tank surrounds the coal bunker and can carry 24,000 plus gallons of water. The coal bunker can hold 32 tons of coal. A fully loaded tender weighs in at a hefty 427,500 pounds. The coal bunker has angled sides to direct coal into the conveyor screw at the bottom, which is part of the automatic Stoker. Let's have a look at the Stoker in detail. There's a 2-piston steam-driven motor mounted at the front of the tender, with a line of rotating shafts that connect to a gear set at the rear, which turns the auger screw. Large coal pieces fall into the central channel. The auger crushes these pieces to the desired particle size. and also carries the crushed coal forward towards the firebox. The screw is divided into rotating sections, and the containing pipe has ball joints so the tender and engine can move independent of one another while the stoker functions.
The crushed coal bits are pushed up to a pan called the stoker table,
below steam jets. Which are angled towards key areas of the firebox. Valves in the cab control pressure to these jets so the firemen can blow coal to specific areas as needed, for fine-tuned control over the coal bed and resulting fire. Steam locomotives are impressive in so many ways. They balance potentially dangerous, powerful reactions into a beautiful, rhythmic, breathing machine that's easy to appreciate in its own right. No matter our accompanying views on the modern world that made them.